Okay, so where were we? My main goal, or I shouldn't say my main goal, but the ultimate goal, I should say, is to prove this inequality. The penultimate goal is going to be to prove this claim right here. That if I have a set of functions going from k equals 1 to n, and I have a function f that I want to approximate as a linear combination of those functions. So remember the linear span, the linear span of these functions form a vector space, subspace. And so I want to approximate, find the function in this subspace that is the best approximation to f. And that's what I mean by best approximation is what I have here. And my claim is that the ck should be given by the inner product of f and phi k. Okay, and again, as I've said before, in our context, the phi k's are going to be sines and cosines, and this is the inner product. But this is such a general fact, I don't want to prove it, like I don't want to write it where I'm writing things with integrals, because it's such a general fact for any Hilbert space. So I only want to use Hilbert space notation. But if you get a little confused about what's going on, like if this confuses you and you want to remind yourself that it's that, just instead of writing that, write this. 1 over pi times the integral of f times phi k. Okay. So all we're going to do is we're just going to compute this. And remember that the norm squared is just the inner product of a function with itself. Now, the first few steps of this is just going to be a whole lot of tedious algebra. I'm going to do it all down here, and I'm going to kind of be erasing and rearranging as I go because I don't have unlimited board space. Okay, but if I just compute this, I'm going to compute the inner product of this function with itself. Okay, and now for ease of notation, I'm going to call this f tilde, meaning the approximate. The approximant. Okay, so if I do this, it's f, the inner product of f minus f tilde and f minus f tilde. Okay, so now I'm going to use the linearity in each part of this to write this out as the following. This is going to be the inner product of f with itself. Okay, then it's going to be minus the inner product of f and f tilde. So that, and then minus, and then minus the inner product of f tilde and f. And then plus the inner product of f tilde with itself. Okay, and so let's write out what each of these are going to be here. Well, the inner product of f with itself, this is just the norm of f squared, so I'm going to keep that. Okay, so let's think about what's going on here. The inner product of f and f tilde, and the inner product of f tilde and f. Well, notice that the inner product we've defined here is symmetric. Now, if we're dealing with a complex inner product, we'd have to have a conjugate there, and we'd have something similar being true. But if we're dealing with a real inner product, then f tilde f is equal to ff tilde. So this is going to be minus 2 times ff tilde. So this is minus 2 times the inner product of f, and I'm going to write out what f tilde is. Ooh. This is going to be equal to the sum k equals 1 to n ck phi k. Okay, and for this last part, it's going to be the inner product of f tilde with itself. And this will make sense in just a moment. But I'm going to use k, the index k's for this first factor. And then for the second factor, I'm going to use index L. Okay, so all I've done is I've just rewritten what this all is. I've just kind of expanded out what this is. So let me remind you, this is equal to this. Okay, so let's do some more rearranging. So this is the L2, or the norm squared. Again, using linearity in both components of the real inner product, this is going to be minus 2 times this sum, k equals 1 to n ck f vk. Okay, and now we're about to get to the step where we can kind of make our first real observation using orthogonality. We haven't used orthogonality yet. But what's going to happen over here? Well, again, it's linear in both of these, so I can pull both of the sums out. And so this is going to be equal to the sum k equals 1 to n, the sum L equals 1 to n, ck, cl, and then the inner product of phi k and phi l. Is that going off? Sorry. Oh no, I just realized that I must have bumped the camera or something and didn't realize it. Sorry, I apologize that it's all like, gummit, I thought I'd fix this. Hold on. This is driving me, this is too tilted now. I thought I had this fixed. That rustle you hear, I'm folding a piece of paper. Slightly better. Okay, so let's look at this sum right here. These are good to go for now, but this sum right here, the phi k and the phi l are orthogonal. So if I forget about the outer sum and I just look at the inner sum, this inner sum is only going to be non-zero when L is equal to K. So in this inner sum, the only term that's not zero is going to be the term where L is equal to K. In which case the inner product there is equal to 1 because the functions are orthonormal, and we're going to have CL or CK times CK. Okay, so now what I'm going to do, what I'm saying is, I'm about to erase this. What this whole sum is equal to this. Okay, so now what I'm about to do is I'm going to erase everything from here, and I'm going to take this and copy it up there. So that's what I'm going to do now. So if you need to look at that, pause it and look at it now. Okay. So this is equal to the norm of f squared. I'm going to write this first. So I'm going to write this as plus the sum k equals 1 to n ck squared. And notice this sum is also going from k equals 1 to n. So I can just combine this into one sum. So this is going to be minus 2 times the inner product of f and phi k. All right, so now what I have here, I have something. So again, I'm trying to find the ck's that minimize this. I want to find the ck's that minimize this, expression. So I have, when you're minimizing something, it's one of the things that you can try to do is to write things as positive terms, and then make those terms zero. Because if I have a sum of positive terms, how do I make that sum small? Well, I make all of the terms zero. Okay, if I have a sum where the terms, some might be positive and some might be negative, if they're all equal to zero, then of course the sum is going to be equal to zero. But if I only have control over some of them, then it doesn't really make sense to set some of them zero and some of them not zero, because you might be getting rid of some cancellation. Now I realize that was kind of confusing, but think about that after I do what I'm about to do here. So what I'm going to do is I'm going to complete the square on each one of these terms. And so now this is going to be equal to the norm of f squared plus the sum going from k equals 1 to n. So completing the square here will give me ck. There's a c. I forgot the ck. There was a ck there that I didn't write down. So ck minus. That was probably really annoying if you were confused for about a few minutes until I got there. I apologize. So it'll be this, and then minus okay, all I'm doing there is completing the square. Well, this then is equal to the norm of f squared minus the sum k equals 1 to n f phi k squared plus the sum k equals 1 to n ck minus the inner product of f and phi k squared. Okay, so what's going on here? This is positive and it doesn't involve the ck at all. This part here, we're minus and negative, it doesn't involve the ck's at all either. So whatever the ck's are, so this right here, everything's are equalities here. There's no inequalities. So this norm right here, no matter what the ck's are given by this expression here. And no matter what the ck's are, this part is always going to be the same. And so the only place where the ck's show up are going to be over here. So in other words, basically this right here is, this right here is what we have control over. This is the thing that we can minimize by choosing ck's. Well, each one of these terms is positive, or non-negative. And so since each of the terms is non-negative, the way to make this sum the smallest is to make ck equal to the inner product of f and phi k. Okay, now, if these terms could be negative, then we wouldn't want to make them 0. We would want to make them more negative so that this is now going to be, even smaller. Okay, but since they're positive, the smallest that we can make this sum here is to make each one of these terms equal to 0. In other words, ck is equal to the inner product of f and phi k, which is exactly what we have here. Okay, so this is kind of the penultimate thing that we wanted to prove. Okay, so how do we get Bessel's inequality from that? Well, let's go back up to this equality here. So now I'm basically going to erase all of this and copy this line up here. So this quantity here is equal to this, the norm of f squared minus the sum k equals 1 to n f pk squared plus this. Well, we've chosen the ck's so that this term is equal to 0. So if we choose the ck's correctly, if we choose ck by this choice here, this term is just equal to 0. And so the error then is going to be equal to this part right here. Again, if we choose the ck's in the right. If we choose the ck's to be this, if we define the ck's to be this, then the error in approximation is going to be given by this expression here. Okay, well, this is the norm squared, okay? So it's greater than or equal to 0. So it means that this quantity here is greater than or equal to 0. Right, this quantity is equal to the error term. The error term is greater than or equal to 0. Whoops, I got this wrong way around. So this right here is greater than or equal to 0. Well, now we just rearrange the inequality and put that sum over there, and what we end up with is the sum k equals 1 to n f phi k squared is less than or equal to that. Okay, so how are we going to apply this? Oh, sorry, we're actually not done. So I've only proven this. I've only proven that the sum from k equals 1 to n, that this holds for any n. Okay, so how do we go from that? How do we go to this inequality for all n to the inequality that we want, which is when we have an infinity there? Okay, so that next part going to be the following. So let's define a sequence of real numbers. We'll call this sigma sub n. Now, what do we know about sigma sub n? Well, we know it's bounded. Whatever n I put here, no matter what n I put there, it's always going to be less than or equal to this quantity here, to this norm, the integral of f squared. This doesn't depend on n. So I know this is always bounded above, and it's positive or non-negative. So I know it's bounded below. So in other words, I have my sigma n sequence is bounded below. Or sorry, it's bounded. It's bounded below and bounded above. But I also know that it's in an increasing sequence. Because what is the difference between sigma n plus 1 and sigma n? It's just adding another positive term. So sigma n is a positive sigma n is a bounded, it is positive, but it's a bounded increasing sequence. And so therefore this sequence has a limit. But the limit of this sequence is just equal to the sum of the series. I mean, by definition, this is equal to the limit of by definition, this right here with an infinity is equal to the limit of these sigma n's. And so that's where the equality comes from. I know that the limit of sigma n, so again, just to be clear, by definition, this series, is equal to the limit of the sigma n's. I know this sequence, the limit of this sequence exists because this sequence is bounded and increasing. So by the monotonic convergence theorem, this sequence converges. And since every term is less than or equal to this, it means its limit is less than or equal to that. And so that's where this comes from. Okay, now where we're going to use this. How are we going to use this when we prove convergence of Fourier series? Well, if I know that the sum k equals 1 to infinity, if I know this is less than infinity, in other words, it converges, then by the test for divergence, this tells me that each one of these terms goes to 0. Okay, and so what this is going to imply is that if you have a function that is square integrable, in other words, like you can take, this is finite. If you do the integral of f squared, it's finite. So if you have a square integrable function, it means that the Fourier coefficients are going to go to 0. And this is going to come up in the proof of, this is one place where the Bessel's inequality will come up in the proof of the the proof of the everywhere convergence of Fourier series for a function that is continuous and differentiable and satisfies this other boundary condition that I was telling you about in one of the previous videos. Okay, anyways, that's it for this video. I will make that video later.